Hello and welcome to another daily Leetcode challenge. Let's begin question 111, minimum depth of binary tree. Given a binary tree, find its minimum depth. The minimum depth is a number of nodes along the shortest path from the root node down to the nearest leaf node. Note, a leaf is a node with no children. Okay, so we're given a binary tree. It's not said to be a complete binary tree or ordered in any particular way, and we don't even care about the values. We just care about what is the shortest, the minimum path to a leaf node. So the minimum path from the root to any leaf node. And another word for that is the minimum depth. Okay, so let's see, from here, I can see that the minimum depth would be 1. If this wasn't here, I wonder if this would be the depth. If the 9 wasn't here, would the minimum depth be 3, 20, 15, or just 3? Well, it says here that the minimum depth from the shortest path from the root node down to the nearest leaf node. So 15 would be the first, or 7 would be the first leaf node. 3 would not be a leaf node. So let's make a decision. Let's make a decision of whether we want to use breadth first search or depth first search. Well, a depth first search, we would have to iterate over all of the nodes, and potentially at some point we will encounter not even potentially, we are guaranteed to encounter the smallest depth at some point. However, thinking now that we do have to then iterate over the whole tree, we have to do 3, 9, 3, 15, 3, 7, and then at some point we might hit that smallest depth, minimum depth. But what if we go breadth first? Well, if we go breadth first, we're looking at a level at a time, starting with the first level and going on to the second and the third and so on. As soon as we hit a breadth or a level that has a leaf node, we are considered to have reached the minimum or have found the minimum depth of the binary tree. So at this point, it's definitely going to be a BFS, breadth first search. Let's implement the breadth first search. Breadth first search is usually implemented with a queue, and I'm going to use a DQ. A DQ is a data structure in Python that lets you NQ and DQ or very easily append to the left and to the right. And this is also could easily be done with a regular list, but it just seems to be the standard. So what we need to do to iterate over breadth first search is pretty much just the queue. However, there's going to be a modification to this simple algorithm, which would go something like this. While queue node equals queue pop left, and then at some point, yeah, we would queue do append node left, then queue append node right, and so on. There has to be a modification to this. The modification is that we need to go a level at a time. And if we're going a level at a time, we need this temp queue that is going to be just a list, actually, because we don't need it to be a DQ. And what we're going to be doing here is we're going to be actually populating the temp queue, and only in the case when, so if not queue, if we have finished iterating over the level that we're currently on, then we would say that queue is equal to, and we can use n for n in temp queue. We can use the spread operator to, or this way of doing a spread operator to copy the content of temp q into q, set temp q to none, and say depth. We also need depth. Start depth at 1, and iterate over and increase the depth by 1. So what this setup allows us to do is we first take note of the first level that we're worried about, that being the root. While our main queue is not empty, we're going to pop its leftmost node, because we have to do it in order. Although this doesn't really even matter. It could honestly just be actually, yeah, it could. We could be popping. We could be popping and then appending. So what if we just do pop? Yeah, that could be better. And actually DQ, I don't know how under the hood it takes care of this. Maybe it's implemented with a linked list, but pop would not rewrite. Pop 0 would have to rewrite all of the elements that are preceding the 0, whereas pop regular would just get it from the rightmost element. So we could be going 3, 20, 9, 7, 15, and it wouldn't matter. And so now that we have this element, we go, we see if we actually, well, let's see, do we need to worry if this is an actual node or not, or will we just be, this is what I'm thinking. First step is check if this is a leaf node. If, and we can do that by not left or node right. So actually if node, meaning that if the node is not a none, if this is a leaf node, if node left, node right, then we can say return depth. So we would have to be returning the depth, and then we would append the right and the left to that element. So how would this work? 3, we pop node 3, we say if node, and then we check if node left, node right, meaning that if any of these are true, so if node or left, this would be, this in the parentheses would end up to being true, and not true is false. But if in the case where both of these are false, meaning that this is a leaf node, not true would always give us a false. So we actually here return the correct depth. And then we would to temp q append the right and the left. Pretty simple. And I'm wondering if this is good. Here, let's return the depth, and let's see if this runs. This runs correctly, and we seem to be hitting everything. Let's submit. Wrong answer in the case where root is an empty list. Root is an empty list if not root, return, and what do we need to return? Expected 0. Let's use this test case, run this against the test that failed. Seems to pass with a 43 milliseconds, and okay, we're beating a good amount of people, and we got the correct answer. So, I mean, let me run through this one more time, how BFS works and what modification we made to the standard BFS algorithm to solve this issue, or to solve this problem. The BFS approach is you have a queue that grows as you iterate over the current level. So we're looking at level at a time, where Q starts off with the root, and while we're looking at the root, we're appending to the right of the Q its children. We append left and right to its end. Then, since Q would no longer contain root, we would start iterating over the root's left node. Root's left node would append root left, left, root left, right, and so on until you continue iterating over the whole tree and eventually run over all of them. In this case, we have to look at level at a time, and the only modification here is this notion of a temporary queue, which is basically just used to indicate when a set of children have been collected for a certain layer. So in the first case, in the first iteration over this whole logical loop, is the root's children get appended to temp Q, and then when we see that Q is now empty, meaning that the root is gone from that Q, we replace Q with temp Q, and on the second, the children of the root's children get appended to temp Q, and so on until we have iterated over everything. And yeah, at this point, this solution is pretty valuable, and it beats a lot of previous solutions. So yeah, I would say use this, and thanks for watching. Have a good day. Bye.